Right now, as you sit here, something is passing through your body. Not radiation, not light, not air. Something with mass. Something that interacts with gravity. Something that, by the best calculations we have, makes up more than a quarter of everything that exists in the universe. Dark matter. We can't see it. We can't touch it. Every detector we've built to catch it has come back empty. And yet the evidence that it's there, everywhere, right now, moving through walls, planets and you, is so overwhelming that the entire cosmological model of the universe depends on it being real. The longer scientists look for it, the stranger the story gets. The story begins not with a particle physicist in a lab, but with an astronomer named Vera Rubin, working in the 1970s at observatories in Arizona and Washington. Rubin was measuring how fast galaxies spin. Not the whole galaxy, individual stars within it, at different distances from the galactic center. Her expectation, and the expectation of everyone in the field, was straightforward. Stars closer to the dense, bright center of a galaxy should orbit faster. Stars out at the dim, sparse edges should move more slowly. This is exactly how planets behave in our solar system. Mercury races around the sun. Neptune crawls. The physics is clean and well understood. It follows directly from Newton's laws, confirmed by centuries of observation. What Rubin found destroyed that expectation completely. Stars at the outer edges of galaxies were moving just as fast as stars near the center. In some cases, faster. And when she mapped galaxy after galaxy, the result held everywhere she looked. The rotation curves, graphs showing orbital speed against distance from the center, were flat. Stubbornly, inexplicably flat. For the numbers to work out, there had to be vastly more mass in those galaxies than what we could see. Not a little more. 5 times more. The visible stars, gas, and dust, everything we can actually observe, accounts for only about 1/6 of the gravitational mass that the rotation curves demand. Think about what that means. You look at a galaxy, you see the stars, the glow, the spiral arms. You think you're looking at the galaxy, but what you're actually seeing is a tiny lit fraction of something much larger, a vast invisible structure that the visible matter is embedded in, the way a handful of glitter is embedded in a dark sphere of glass. The rest is dark, the rest is invisible, and the rest is holding those galaxies together. This wasn't a small anomaly in one galaxy. It was a signal repeating across hundreds of galaxies Rubin and her colleagues examined. The universe was telling us something enormous, and what it was saying was this: most of what exists, we cannot see. Rubin herself put it plainly. She said the universe is mostly made of dark matter, and that we have but a small fraction of the universe in luminous matter. She said it calmly, as a fact, because by then, to her it was. Take a moment to feel this number. Of all the matter in the universe, everything that has mass, everything that responds to gravity, everything that makes up the substance of the cosmos, about 85% is dark matter. The atoms, molecules, stars, planets, gas clouds, and black holes we can detect, all of that is the remaining 15%. We have spent centuries building an understanding of matter. We discovered atoms. We split them. We found the particles inside: protons, neutrons, electrons, quarks, neutrinos. We built the standard model of particle physics, one of the most precisely tested theories in the history of science. We mapped the periodic table. We understood chemistry, biology, nuclear reactions, the interiors of stars. And all of that knowledge, every particle we've ever detected, every element we've ever named, applies only to 15% of the matter that exists. The dark matter doesn't emit light. It doesn't absorb light. It doesn't interact with the electromagnetic force at all, as far as we can determine. The only reason we know it's there is gravity. It bends space-time. It pulls on things. It clusters and forms structures that the visible matter falls into, like rocks rolling into invisible valleys carved across the cosmos. The current cosmological model, called lambda CDM, the standard model of cosmology, actually requires dark matter to exist. Without it, the equations don't produce a universe that looks anything like ours. The large-scale structure of the cosmos, those vast filaments and walls and voids we've mapped across billions of light years, only forms the way it does if there's a dark matter scaffolding underlying all of it. The visible universe is, in a very real sense, a decoration on a structure we cannot see. Dark matter didn't just shape individual galaxies, it shaped everything. The arrangement of matter across the entire observable universe, every cluster, every filament, every void, is a fossil record of how dark matter moved and clumped in the first hundreds of millions of years after the Big Bang. We live inside a sculpture made of something we've never detected. Here's where it gets genuinely unsettling. For decades, physicists had a leading candidate, a particle called a WIMP, a weakly interacting massive particle. WIMPs made elegant theoretical sense. They were predicted by supersymmetry, a framework that extends the standard model of particle physics, and was, for a long time, considered one of the most promising directions in theoretical physics. WIMPs would have mass. They would interact via the weak nuclear force. And crucially, the Big Bang would have produced them in roughly the right quantities to explain the dark matter density we observe today. This was called the WIMP miracle. The coincidence seemed too perfect to ignore. So physicists built detectors. Extremely sensitive detectors, buried deep underground to shield them from cosmic rays, cooled to temperatures near absolute zero, watching for the faint nuclear recoil that would indicate a dark matter particle colliding with an atom. These machines are marvels of engineering. The LLUX Zeppelin detector in South Dakota sits nearly a mile underground, filled with 10 tons of liquid xenon, sensitive enough to detect a single electron knocked loose by a passing particle. The detectors found nothing. The LHC at CERN, the most powerful particle accelerator ever built, smashed protons together at nearly the speed of light, creating conditions designed to produce WIMPs if they existed. It ran for years. It found the Higgs boson. It did not find dark matter. Experiment after experiment returned null results. The WIMP parameter space, the range of masses and interaction strengths where WIMPs were expected to hide, has been searched exhaustively. What was once the leading candidate has been squeezed into an increasingly narrow corner. The WIMP miracle is starting to look less miraculous. We haven't ruled it out entirely, but we've eliminated vast swaths of the territory where it was supposed to be. Other candidates have been explored. Axions. Extremely lightweight particles first theorized in the 1970s to solve a completely different problem in quantum physics. They're so light that a single kilogram of them would contain more particles than there are stars in the observable universe. Experiments like ADMX and HAYSTAC are searching for them now, but the search space is enormous and the signal desperately faint. Sterile neutrinos, hypothetical cousins of the neutrinos we know exist, but even more reluctant to interact with anything. Primordial black holes. Black holes formed in the chaos of the early universe, before any stars existed, which could theoretically account for some portion of dark matter without involving any new particle physics at all. The LIGO gravitational wave detectors have put limits on how many of these could exist. Not zero, but not enough to explain everything. Each candidate has been partially constrained. None has been confirmed. The list of things dark matter is not keeps growing. The list of what it might be keeps shrinking. It would be tempting to dismiss dark matter as a theoretical construct, a convenient placeholder for something we don't understand. But the evidence doesn't come from one observation or one calculation. It comes from completely independent lines of inquiry developed by different teams, using different instruments, studying different phenomena across vastly different scales. And they all point to the same answer. Start with gravitational lensing. Light doesn't travel in straight lines when it passes near something massive. Gravity curves space-time, and the light follows that curve. Einstein predicted this. We confirmed it during the 1919 solar eclipse. But the effect scales with mass, and at the scale of galaxy clusters, it becomes dramatic. When light from a distant galaxy passes through a foreground cluster, it bends, stretches, and sometimes splits into arcs. By measuring how much, astronomers can calculate the total mass doing the bending, regardless of whether that mass glows. When they do this calculation for cluster after cluster, the result is always the same. The visible mass, all the stars, all the hot gas, everything that emits or absorbs any form of radiation, accounts for only a fraction of what the lensing demands. The rest is there. It has mass. It bends light. It just doesn't interact with that light in any other way. The bullet cluster is perhaps the single most striking piece of evidence we have. It's a pair of galaxy clusters that collided roughly 150 million years ago. A cosmic collision so violent, it's one of the most energetic events ever observed since the Big Bang itself. When two clusters collide, the gas, which makes up most of the visible mass, behaves like a fluid. It slows down due to electromagnetic interactions, heats to hundreds of millions of degrees, and glows brilliantly in X-rays. It piles up in the middle of the collision zone. But dark matter doesn't care. It barely interacts with anything, including other dark matter. So while the gas breaks and compresses at the collision point, the dark matter in each cluster passes straight through the other cluster as if it weren't there. Astronomers mapped both components simultaneously. The hot gas, visible in X-ray observations from the Chandra telescope, sits between the two clusters, slowed, compressed, exactly where the physics of a collision predicts. The gravitational mass, revealed by lensing, is offset to either side, still moving outward, ahead of the gas, detached from it. The dark matter punched through the collision and kept going. This is not a statistical inference. It is not a model-dependent conclusion. It is a direct, visible spatial separation of dark matter from ordinary matter, captured in a single image. You can point at it. That image has arguably done more to silence dark matter skeptics than any other single observation in the field. And then there's the cosmic microwave background, the faint afterglow of the Big Bang. Light that has been traveling toward us since the universe was just 380,000 years old, when it first became transparent enough for photons to move freely. The CMB is not uniform. It has tiny temperature fluctuations, hot spots and cold spots, at the level of 1 part in 100,000. These fluctuations encode the physics of the early universe with extraordinary precision. Those fluctuations are not random. They have a specific statistical pattern, peaks and troughs at particular angular scales, that depends sensitively on the composition of the universe at that early moment. The ratio of normal matter to dark matter leaves a precise fingerprint in that pattern. When cosmologists fit the CMB data, and the Planck satellite measured it with astonishing precision, the best fit requires dark matter. Not approximately, exactly. Remove dark matter from the model, and the predicted CMB pattern looks nothing like what we observe. Add it in the quantities suggested by galaxy rotation curves and gravitational lensing, and the fit is near perfect. 3 entirely separate methods. Rotation curves from the 1970s. Gravitational lensing of galaxy clusters. The temperature pattern of the oldest light in the universe. Developed independently by different communities over 5 decades. 3 consistent answers. Dark matter is real. The question was never really whether it exists. The question, the one that keeps physicists awake, is what it actually is. Before we go further, it's worth acknowledging the other option. What if dark matter doesn't exist? What if gravity itself behaves differently than we think at large scales? This isn't a fringe idea. There is a framework called MOND, Modified Newtonian Dynamics, proposed in 1983 by physicist Mordechai Milgram. MOND adjusts the laws of gravity at very low accelerations, the kind found at the outer edges of galaxies where dark matter's influence would be greatest. And remarkably, it does predict flat rotation curves without invoking any invisible matter. For individual galaxy rotation, MOND works surprisingly well. It correctly predicts the Tully-Fisher relation, the observed correlation between a galaxy's luminosity and its rotation speed, with no free parameters. This is a genuine achievement, and it's why some physicists take MOND seriously. But MOND struggles with galaxy clusters, where additional mass is still needed even after the modification. It doesn't naturally explain the bullet cluster, where you can literally see the gravitational mass separated from the visible matter. And it doesn't reproduce the detailed pattern of the CMB without adding extra components that look suspiciously like dark matter anyway. More elaborate relativistic successor theories exist: TeVes, covariant emergent gravity, and others. They're mathematically complex and still face observational challenges. The James Webb Space Telescope has been providing data that some researchers argue puts additional pressure on these alternatives, though the debate is ongoing. The mainstream scientific community has not abandoned dark matter. The convergent evidence is too strong, but modified gravity remains a legitimate area of research. And the fact that we have to consider fundamentally rewriting gravity to explain what we see tells you something important about how strange this situation actually is. We are choosing between two deeply uncomfortable options. Either most of the matter in the universe is invisible and made of something completely unknown, or our understanding of gravity, tested to extraordinary precision in the solar system, breaks down at galactic scales. Both of these require us to revise our picture of reality in a significant way. Here are the questions that remain genuinely open, that physicists are debating right now with no resolution in sight. If dark matter is a particle, why haven't we found it? The underground detectors are now so sensitive they can detect individual neutrinos from the sun. They have been running for years. The silence is deafening. Either the particle is lighter than expected, or heavier, or it interacts even more weakly than even the most pessimistic predictions allowed, or we're looking in entirely the wrong way. Does dark matter interact with itself? The standard assumption is that dark matter particles barely interact with anything, including each other. But some observations of galaxy cluster shapes and merger dynamics suggest that dark matter might have internal forces, a dark force that only dark matter particles feel. If true, there could be an entire dark sector, dark atoms, dark chemistry, dark complexity, a universe of structure that exists alongside our own, completely invisible, evolved over 13 billion years. We would never know. Is dark matter cold, warm, or hot? These terms describe how fast dark matter particles were moving in the early universe. Cold dark matter, slow, heavy particles, is the standard assumption, and it matches large-scale structure beautifully. But at small scales, some observations suggest fewer dwarf galaxies than cold dark matter predicts, and the density profiles of those galaxies look different from simulations. Warm dark matter, lighter, faster particles, might explain this. The data is not yet definitive, but the tension is real. And the deepest question, what if the answer is something no one has thought of yet? Every major revolution in physics came from a direction that wasn't anticipated. Quantum mechanics was not an incremental refinement of classical physics. It was a rupture, General relativity didn't patch Newton. It replaced the very concept of gravity. The answer to dark matter might be equally rupturing. It might require concepts we don't currently have words for. There is something almost philosophical about this situation. We have mapped the universe with extraordinary precision. We know the temperature of the cosmic microwave background to 5 decimal places. We can trace the web of galaxy filaments across billions of light years. We've detected gravitational waves from black holes colliding a billion light years away. Ripples in spacetime smaller than a proton. And yet, 85% of the matter in that universe, the substance that forms its skeleton, that shaped every galaxy that has ever existed, that is passing through your body right now at this very moment, remains completely unknown. We haven't failed to find dark matter because we haven't tried. We have tried everything we know how to try. The failure is informative. It tells us that whatever dark matter is, it is genuinely alien to everything we understand about matter. It doesn't fit in the standard model. It doesn't play by the rules that a century of particle physics built. The most honest thing a physicist can say about dark matter is this: we know it exists. We know roughly how much there is. We know where it lives and how it behaves gravitationally. And beyond that, we know almost nothing. Which means the answer when it comes will not be a footnote. It will not be the discovery of a particle we already suspected, quietly confirming an old prediction. It will rewrite the book. It will change what we mean when we say the word matter. Here is the question worth sitting with. If something that makes up the vast majority of all matter in the universe can remain completely invisible to us, to every instrument we've ever built, every theory we've ever written, for nearly a century, what else might we be missing? Not just undiscovered, not just undetected, but so alien to our current understanding that we haven't even thought to look.